Okay, so for the second talk today, it's my pleasure to introduce Harumichi Nishimura, who will talk about distributed quantum proofs for replicated data. Please.
Thank you. I'm Harumichi Nishimura. This is joint work with Pierre, Fraigniaud, Francois, Gall, and Untitled. In this talk, we consider distributed computing and its quantum version. There are several quantum distributed computing protocols, such as exact leader election, which is impossible in classical case, but quantumly possible. And also, recent years, several problems such as diameter, APSP, are efficiently computed by quantum network rather than classical network. We want to add one more task in this talk. The outline is as follows. First, we introduce our problem. Next, we introduce the setting. And I describe the result, and I present overview of our protocol. Our protocol is the equality of replicated data. Here, the network has several terminals. Terminal means a node who has data. This data is should be same. For example, this is original and this is replicated data. The question is, are all data identical? Because, for example, some node might change from original by some error. So we want to check regularly whether all data are identical or not. But unfortunately, there is no constant round protocol in the network because, for example, this terminal and this terminal is very far. Then we cannot directly send this data to this data. So in fact, omega r round are needed to check. Here r is a diameter of the network. Here in this talk, we assume the nodes do not share prior randomness or entanglement. That's our assumption in this talk. However, there is a one-round NP-like protocol, which is called distributed certification. Now we move to our setting, distributed Merlin-Arthur protocols. Distributed Merlin-Arthur protocol is called several names, proof labeling scheme, locally checkable proof, etc. In this case, as usual NP-like protocol, there is two parties, prover and verifier. But verifier, in this case, verifier is a set of nodes which are connected to edge. So verifier corresponding to a network. Prover always powerful as usual. So he can do everything. But in this case, verifier is restricted so that each node can send only the message to neighbor. The verification scheme has two phases. First phase is prover phase. Prover sends some message called certificate to each node, like this. Of course, each message can be changed, different. Second phase is called verification phase. This is the check procedure by nodes. So each node exchange message with neighborhood. In this talk, this message change is done in one round. Now, I mention the property for Merlin-Arthur protocol. First, we consider the yes-no problem for the yes instance case called completeness. Then there exists some message from prover such that all nodes accept. This is important part in distributed network case because every node must check if the configuration of the network is legal or not. So all nodes must accept. On the other hand, for the no instance case called soundness, every certificate from prover, some node reject with high probability. This is the completeness and soundness in distributed Merlin-Arthur protocols. Now, I mentioned trivial protocol. Prover send X when all data are X. Verification phase, each node just check it is the same as the neighbor's one. So just send the message each other. Clearly, yes case, all node accept by this witness. On the other hand, if no case, which means some node input is different from other. In this case, any witness cannot convince the network. So some node reject. For example, this from if prover send X to all the node, then this part is different. So this node, these two nodes reject. This is the trivial protocol for our problem equality in the network. But this trivial protocol is communication inefficient because prover send the message itself, input itself, so n bit for each node. And also each node send n bit to neighbor. So it's communication inefficient. Now we move to our result, quantum distributed Merlin-Arthur protocols. Our result considers quantum version of distributed Merlin-Arthur protocol. Here, certificate can be quantum message from prover. Also, the each exchanging message are also quantum. Our main result is a quantum upper bound. We show there is a distributed quantum Merlin-Arthur protocol for our problem equality of replicate data with order t times r square log n plus r qubit certificate and message, where t is the number of terminal. So in this case, 3. And also r is diameter of the network. In this case, I think 5 or 6. Important point is T and R typically much smaller than N because N is the length of data. Usually data size is much larger than graph size. So T and R depend on graph size. On the other hand, N depend on the data. So N is the most largest, sometimes exponentially large factor. So this part is logarithmic, is our sales point. On the other hand, classical lower bound, it is very easy to show. We show that any DMA protocol requires omega n bit certificate if error probability is reasonably small. This is our result. Now we move the overview of our protocol. From here, we consider only the path networks for simplicity. But in fact, our protocol for general network is obtained by a combination of the protocol for passes, which I explained from here, and classical distributed Merlin-Arthur protocol, such as certifying spanning tree. Now, path network is very simple. Just 2 terminals, left end and right end. These 2 nodes only have input. And also our diameter is exactly the same as the path length. So we consider one round protocol. So every node sends the message neighbor simultaneously. So this and this is simultaneous. Now we consider the classical case for 2-node case. For the case 2-node, this node and this node can directly communicate. So we can use hash function and we can construct communication efficient protocol. X randomly chosen H hash function and send hash function and hash value. On the other hand, Y also randomly chosen another hash function and send hash function and hash value. Then Y knows hash function H, so he can create HY. So check HX hash value to hash value is same or not. Of course, X equal Y, then hash value is same. On the other hand, X is not Y, the hash value is not same with high probability. And also the length of hash value, hash function and hash value is order log n. But if the path length is more, 3 or more, then similar strategy is impossible. because the left node and right node cannot communicate directly in one round. In particular, the case of 3 node is similar to simultaneous message passing protocol, so-called SMP protocol in communication complexity, because the central node has no information on input and her simultaneous message is useless. So like this, this guy is sent to the referee, and also this guy sent to referee. And also the classical case, prover does not help much because, for example, we can consider first prover send hash, choose a randomly hash function and send hash and hash value to central node, and central node send to this message to both ends. Then this seems work to check the equality of x and y, but note that prover may be malicious. So prover may not randomly chosen. Prover does not choose hash function randomly. So this is a problem. In fact, we can show classical lower bound omega n for prover's certificate size can be proved for the path of 4 nodes. Now we move to our quantum protocol. Before our protocol, we explain the basic tool. Maybe you can, as you can expect it, we use quantum fingerprint and subtest by famous paper Berman, Cribb, Watras, and Dwarf. In fact, quantum fingerprint is the uniform superposition of the hash and hash function and hash value. This is, of course, order log n qubit state. And if x is not y, then these two fingerprint almost orthogonal. To check the orthogonality, we can use subtest. So the BCWW show essentially order log n qubit are enough for 3-node case without prover, because 3-node case is similar to SMP protocol in communication complexity. Now, our protocol in more many node case use quantum fingerprint as certificate. Now we move our quantum protocol. First, prover phase. Honest prover when x equal y, send certificate fingerprint of x or y to each node of the intermediate node like this. And left node create his own fingerprint and also y own fingerprint. In fact, this and this same. And verification phase, first we each node choose flipping the coin, and if coin is 0, then send the state to right node. On the other hand, keep itself. Each node does subtest. If it has two states, for example, this node coin flip is 1, and this node coin flip 0, then this guy has two states, then he does subtest. And if reject case, the result is reject. Otherwise, accept. Now, we move to analysis. Clearly, if x is equal y, then all nodes accept with probability 1, because now all nodes have hx, because x equal y. So every subtest pass. On the other hand, x is not y, then the probability that all nodes accept is 1 minus omega 1 divided by r squared. In fact, prover can send the entangled state because he is malicious. But, and also soundness error, this is a little bit large, but we can reduce to 1/3, for example, by order R square repetition as standard way. Now we mention the soundness. We want some node to reject subtest with probability 1 over R square. To show this, we use the following property. If subtest accept on input row AB, here like this, to reduce state, this trace out one part, row A and row B must be close. So if we trace out this part and also this part to reduce state, it must be close. This property we use. Then, assuming all nodes accept with high probability, then Hx close to the reduced state of node 1, and also reduced state node 2, etc., etc. Then the two fingerprint must be close, which contradict they are orthogonal. The fact they are orthogonal. So some node must reject with some probability. That's our strategy for showing the soundness. Now I summarize my talk. We introduce distributed quantum Merlin-Arthur protocol, and we consider the problem equality of the replicated data. We show there is a distributed quantum Merlin-Arthur protocol for this problem with relatively small size quantum certificate and message. It is, on the other hand, any distributed Merlin-Arthur protocol require omega n bit certificate. So this part and this part has exponential gap. Our remaining future work is first, we only consider this problem. So can you extend the distributed QMA protocol for other problems. And second, and more important open problem is lower bound. We don't know any lower bound for distributed quantum Merlin-Arthur protocol. So any lower bound is welcome. That's all. Thank you very much.
Okay, thank you very much. So I'm still monitoring the Slack channel for questions. So far, there are none from there. But I had one, maybe you mentioned that, so you only gave us the proof for simple graphs. Maybe you can say something about what you need to, what is the additional difficulty in generalizing it?
Yeah. So in general case, not the line network, but in general network, we consider the spanning tree, and spanning tree is easily checked by classical strategy from the prover send some message, and each node can check they have spanning tree or not. Then we can consider some tree. So some root sent to leaf, then we can reduce this tree case to line network case. So
okay.
Basically classical strategy we have.
Yes. Okay, so we have now one question by Yvke. The soundness area is still pretty big. I imagine you can make this area smaller by repeating the protocol the number of times, or is that how you deal with this?
Sorry.
So the soundness area is still pretty big. 1 minus 1 over r squared, right?
Soundness error is oh, sorry, 1/3. So
okay.
So original
by repetitions.
Yeah, we can use parallel repetition. So
okay.
That's no problem.
And so what? Yeah, the question is essentially what does that do to the message size? It's just r squared times the.
Yeah. Message size is this. This part is by come from parallel repetition.
Okay.
But this it is this part is different from classical low bound, but in fact T and R is usually much smaller than N. So we consider this part is log is much better than this classical low bound.
Oh, okay, but for some.
Yeah, of course.
Okay, for some networks, it will actually be more. The cost will be higher.
Yeah. T and R is if we consider the case T and R is as same as N, then this bound is not good.
Yes. Okay. Okay. Yeah. Thank you very much for these additional explanations. And yeah, so there are no further questions, and then maybe we let the next speaker, Pierre. Thank you very much.
Thank you.